So most of the things like in here and in here, you've seen it before in your thermodynamics, aerodynamics courses. So that's not very uh, hard for you to remember those stuff, especially from this Euler equation for turbomachinery. So if you remember, we had a perfect gas, and as we had these assumptions are there to enable us to use the kinetic theory of gases. What are those assumptions? First assumption was that have negligible or a small amount of intermolecular forces between molecules. And then we have the volume of molecules that occupies space, also negligible, and we usually ignore it. Based on these assumptions, we come up with the perfect gas law, and this perfect gas law is actually derived from the kinetic or kinetic theory of gases. You remember this also from early studies in physics. E is equal to rho RT. And what is R in here? R is the gas constant, and it is defined by the universal gas constant divided by the molecular mass of the gas. M is the molecular mass, and the RU is universal gas constant is equal to 8.314 kilojoule per kilomole Kelvin. As another reminder, you had these specific heats for a perfect gas. So PG stands for a perfect gas, and also calorically perfect gas. Remember, you had in your thermodynamics, aerodynamics, and define a specific heat at constant pressure and volume. For example, if you use your enthalpy, you define pH as the multiplication of the specific at constant pressure by your temperature. So, and in general, we were saying that your Cp, specific constant temperature, is a function of temperature. And the same applies to the internal energy or energy, and it's equal to Cv dt. So Cv is the specific heat at constant volume, and that is also a function of. And there is a simplifying assumption of constant specific. So whenever we say Cp is constant, Cv is constant, we generally simplify this because these are a function of temperature. But if we are dealing with a narrow temperature range, assume that for a calorically perfect gas, these two will be constant. As an example here in the jet engine or turbojet engine, you see the compressor blades in here. These are the compressor blades. There you see the combustion chamber, and then there is the expansion in the turbine blades, as you can see. And when you look at the distribution of, let's say, temperature, the blue one is the distribution of temperature from the inlet of the engine to the outlet of the engine, exhaust of the engine. If you look at the distribution of temperature, you see that the temperature is gradually increasing inside the compressor from, let's say, 0 degrees centigrade until something like 500 degrees centigrade in here. So this is a change from 0 to 500 degrees. And then suddenly in the combustion chamber, it jumps to near 1000 degrees, and through the combustion, we can find that it is again constant. And then in the turbine, you can see that the temperature is reduced to again something like. Then at the exhaust, it is constant. So the temperature is variable in here. For us to do the calculations, preliminary calculations mainly deal with the constant values. You go to the combustion, you assume the constant values for CP. Just keep this. Okay, let's have a brief look at the first law, second law, combination laws of thermodynamics. Remember that you had the first law when you apply this first law to a closed system. What do I mean by closed system? That the system that is not interacting with the environment. You remember that you had delta Q minus delta W equal to dE. This is the first law. What is delta? Delta means something that is path dependent. So it depends fully on the path of the process that it takes. But when we deal with the energy, then we don't use delta, we use D, differentiation, because the energy is not path dependent. So as I write here, the delta Q is the heat added to the system, and it is path function, so that is dependent on the process. Delta W is the work done by the system. It is also path function, and the dE is the total energy change in this. Is a point function. So this total energy is actually the summation of what? Internal energy, kinetic energy, and potential energy. So we have these three together. But when you look at this first law in an open system, the open system is a system that is contracting with the environment. So it has some inlet, it has some exit, like the jet engine I previously showed to you in this slide. You have this inlet, and at the end you have this exit. So you have to use the open system shape of the first law. What is changing when you compare it to the closed system? Actually, for open system, you write everything the rate. So what do I mean by rate? Rate means bugün. Hı hı. Evet. Ben şu an ders kaydediyorum da bu bitince ben de problem değil hocam. Kusura bakmayın. The rate is ddt. We are using this ddt or the rate for all of the elements in the closed system. So let's first start with the right hand side of the closed system. So we're gonna write the rate of accumulation of total energy inside the volume. So dE over dt. Then forget about just right now. Forget about this part and flux part. We will go to the left hand side. So left hand side you have delta Q and delta W, and we're gonna write them in rate format. So dot sign here, delta Q dot, and also delta W, delta W. So these two terms, and we said that there is an open system, so it is interacting with the environment, so it has inlet and exit. So this inlet and exit, they both show themselves in the flux. So this is the term that we are using as inlet minus exit. What is it? is the mass flux of inlet times the enthalpy times the kinetic energy times the potential energy. And again, you have mass flux of the outlet times the enthalpy kinetic energy. This is the representation of the first law applied to an open system. Now let's look at the second law. And as you know, a statement of impossibility of heat engine, the heat engine, the exchanging heat with a single reservoir, producing mechanical work continuously. Actually, the second law says that you cannot have a machine that is just interacting with one source of heat and then gives you some mechanical work. Necessary having a second reservoir at lower temperature where heat is rejected to by the heating. So you remember from your thermodynamics that you have some heat engine. It absorbs some heat from your source, and then it gives the heat to a sink, and you remember that it gives you some work as well. So this is the representation of all mechanical work may be converted into system energy, whereas not all heat transfer to the system may be converted into system energy. And based on this, you have the Clausius inequality. You remember TdS is always greater than or equal to your delta Q. So what do we have in here? We are not talking about work. So the second law actually distinguishes between the work and between nothing to do with the work. So this is the difference between the first law and the second. Actually, in the first law, you have no distinction between the heat and mechanical work exchange with the system, but in the second law, you actually saw that it only has the uh, value of the heat, so you have distinguishing between heat and work. So if you combine the first law and the second law, what will you get? You get Gibbs equation. Remember. We have the pressure forces within the fluid perform reversible work, and the viscous stresses account for dissipated energy of the system into heat. So if you write it as PdS equal to dE plus PD nu, and then you define your enthalpy as combination of the two forms of fluid energy. One is internal energy, and the flow work, which is P nu. And you remember that you could write your changing the enthalpy as dE plus PD nu plus nu dP, and then if you take this dE to put it in here, you will come up with the last equation, which is equation is very important, so keep it in mind. Then when we are using the Gibbs equation, you can come up with the entropy change in the process using this Gibbs equation. How? You can define the entropy change as Cp dt over T minus nu over T dP, and then you can find you can integrate both parts of this, and you will come up with S2 minus S1 here as the change of the entropy delta S, and in the right hand side you have integration from point 1 to point 2 of this term and this term. So what happens to these two terms? For calorically perfect gas, remember that this in a narrow temperature is constant, so Cp comes outside of this integral. So you have Cp ln of T2 over T1 minus R ln of P2 over P1. But for a non-calorically perfect gas, Cp stays there inside. What do we do exactly with this? We actually take Cp at zero point 0.1 and take another value at zero point 0.2, so we're going to have two different values at zero point 0.1 and 2, and these values are actually tabulated in terms of tables. We have the specific heats and also their ratio. Remember, already for these page, and so you can write Cp equal to Cv plus R, and then if you divide everything by R, you're gonna come up with these two equations that are very important to us. C is gamma over gamma minus 1 over R, and Cv is R over gamma minus 1. What is gamma? This is the ratio of your Cv is gamma. This gamma actually is related to the degrees of freedom of the gas molecules. So by this n plus 2 over n. What is n? N is, let's say, for a diatomic gas, diatomic gas. Diatomic gas is something to and etc. For diatomic, because atoms, right? For diatomic gas, which stays at normal temperatures. Normal temperature, what do we mean by normal temperature? The temperature that is less than 600 degrees, we say this is a normal temperature. Less than 600 degrees, you have 3 degrees of freedom. EOF is degree of freedom. Translational motion, so imagine that it can go in X, Y, and Z directions, okay? Translational motion, okay? And also you have 2 degrees of freedom on rotational motion. So, for example, it can rotate about X and Y axis. Therefore, you have 5 degrees of freedom, and if you put 5 instead of 10, you'll come up with 1.4. And you remember this 1.4 in your thermodynamics and aerodynamics courses. Question always says to you that take gamma equal to 1.4. But what happens if you increase temperature? So if your temperature is between 600 and 2000 Kelvin, another mode is activated, which is a vibrational mode. So you have n equal to 6. When n is equal to 6, you have gamma is equal to 1.33. In your courses, maybe in your propulsion gas turbine engine courses, you saw some of the times they are using 1.33 as the gamma for the gas inside the combustion chamber, because the temperature there is so high, then you have 1.33. And above 2000 Kelvin, another mode of motion is used that makes n equals to 7, and then your gamma is again decreased to 1.29. As I said, this specific heats, Cp and Cv, are function of temperature for ideal and real gases. So, and we know that for all of these variation in heat, the temperature is due to vibrational and rotational energy, as we discussed in the previous slide. Now, what I have in here, I have from a thermodynamic book, et al. And in this picture, you can see that for different kinds of gases, like these monoatomic gases in here, argon, helium, neon, krypton, and xenon, and like diatomic gases like hydrogen and oxygen, and for carbon dioxide and water, and also for air, you can see the variation of your specific heat at constant temperature, at constant pressure, with the temperature. And you can see that for the monoatomic gases, it is always constant. It's not mm, depending on the temperature. Why? Because these monoatomic gases are actually their internal energy is contributed by translational energy, only translational energy. So while we said we have vibrational and rotational in other gases, we only have translational energy, that is energy of monoatomic gases. Based on this, these are constant. What are these? These are, we said, these are tabulated in thermodynamic tables. Also, you can use such fittings. So you can fit a function, a polynomial, to the let's say tabulated values and find some coefficients like A0, A1, A2, and stuff, and you can fit a function. So whenever you put your temperature inside, you will come up with your CV at that specific. Okay, that's enough for the thermodynamics and laws and stuff. Now let's go to the isentropic process. From Gibbs equation, you remember this Gibbs equation? How do we came up with this Gibbs equation? And from the Gibbs equation, you can actually come up with this relation. P2 over P1 is T2 over T1 to the power of gamma over gamma minus 1. And if you use the perfect gas law, you can convert this, you can relate the pressure, the density as well. So these are the things that you're remembering from the, and you also familiar with the stagnation state. What is the stagnation state? Is state of zero. It's actually a state of a gas that is reached in decelerating a flow to rest reversibly and adiabatically and without any external work. So you're imagining a gas that you're bringing the gas into rest, so there is no velocity. Stagnation means rest, but there is no external work, and you do this in a reversible process, and also it is adiabatic. So there is no uh, heat, and also there is no work. W is equal to 0, Q is equal to 0. What do you end up with is the definition of the stagnation properties. For example, here you have the definition of a stagnation enthalpy, which is your static enthalpy plus your dynamic enthalpy, squared over 2. So we know that the total energy of the gas does not change in the distillation process. Why do I put this engine in here? Because it's much easier for us to conduct with stagnation properties rather than the static. We are always interested in stagnation or total properties in turbomachinery. And for a calorically perfect gas, if you remember, your Cp is constant, so you can convert these enthalpies to say Cp0, and this is Ct. So if you divide everything by Cp, cancel Cp, T0, which is your stagnation temperature, is your static temperature plus which is your dynamic temperature. Okay, so far we had a brief discussion, brief review of thermodynamics and isentropic processes, states, and these things. So this is kind of view for you. Also, uh, some exercises to do uh, so you can remember everything again. Uh, Now we are dealing with the turbomachinery course, and the first thing that we have to, let's say, consider is the Euler equation for turbomachinery. So this Euler equation, if you consider control volume as it's shown here in red, that encompasses the rotor part. So this is its inside, it's a rotor blade or rotor part. General turbo machine. It doesn't matter whether it's an axial turbo machine, radial turbo machine, whatever you have, considering the rotor part, so it is rotating. How is rotating? It is connected to this shaft, and it is rotating with a rotational speed of omega. So omega is your RPM. So normally in a turbo machine you have your rotor and then there is a casing around the rotor. So this is the casing. And normally you are assuming everything in the cylindrical coordinate system. So cylindrical coordinate system has the axial direction, radial direction, and tangential direction. Axial direction is the direction that flow normally gets inside the turbo machine. This red one, as I said, is the control volume. We have a cylindrical coordinate system, and this line in the middle is the rotation axis. The turbo machine is rotating around this axis by the shaft. And while you are considering this control volume, you have to note that there is no cross mass flow between two streamlines. Okay, so when you have two streamlines like this, there is no cross mass flow, so you can come always following the stream. Again, when we consider this, we consider one input. This is our station 1, and the output. So this is our station 2. And we only consider the flow between inner and outer shells. So it is this control volume is like a shells, and you are considering the flow only in between these two shells. As you can see, this shell, the entrance, station 1, and this is the bigger shell, the exit, station 2. Small shell has the radius 1, big shell has radius 2, right? So let's define properties at the station 1. So at 1, let's define all the velocities. So the axial, the tangential, the radial, and you have your total enthalpy, you have your enthalpy, you have your total temperature, you have your density at 1, and also total pressure and static. The same at station 2, you can define all the velocity components, 1, and total and static enthalpy, total and static temperature, density, as well as total and static. So when you define all of these, you have to assume very important thing. What is it? You have to assume that there is no radial force. Means that your PR is actually zero. PR is zero, but it's not zero. It's very important, though. But in very normal for us to neglect this variation in radius, in radial direction, in our preliminary design. So right now, let's consider that your radial variations is zero. What I mean by radial variation, radial. So it means that flow is not changing, say, by the way, each one of these, let's say, velocity components represents something that is very important. For example, the axial velocity, dz, presents you the mass flow, and it has direct impact on your area of your turbo machine. So it has, when the area is changing, it means that the size of the turbo machine direct impact on your size. On the other hand, you have a tangential velocity. Tangential velocity represents power or torque to you. How? You have force that is applied to the blades. How is it happening? So you have this rotation, okay? And then there is a force, let's say, tied to the rotor blade. These are the stator blades for you. When it is rotating, there is force. And this is your tangential. This tangential force, you remember, if you multiply it by some distance, what is the distance? This is a radial distance from the shaft axis. And then if you multiply it by your RPM, which is your, you'll end up with your power. So E theta actually representing your power output. And at last, your radial variation, or VR, which we right now assume it to be zero, represents all the losses inside turbo machine. So an ideal turbo machine is a turbo machine that has no radial variation in velocity. If there is any loss from your VR, then it means that you have to pay more money. Okay, so far we introduced control volume to you, which encompasses the rotor blade that is rotating. We said that you just to account the entrance and the exit of this control volume, and you can actually write equations motion like the continuity equation, and then angular momentum conservation, and finally you can write the energy conservation and speed. Okay, let's start from the continuity equation. By the way, the derivation of these are not very important. You know, be able to just distinguish the inlet, outlet, and what are the continuity says that whatever comes in goes out, right? So the inlet thing at station 1 and the outlet has the ring at the station 2, just equal them. And Angular momentum, what does it say? Angular momentum actually says that water is nothing but some torque that is applied on the steam tube at the shaft. Like, this is your torque. How? Rho times dV is your dm, and we said that if you have your tangential force divided by radial distance divided by your dm, you will come up with torque. This torque is actually equal to the difference of angular momentum at outlet and inlet. Outlet. So you can say angular momentum difference, the right hand side is why we do neglect. We didn't. We just take the dm dot on both sides, on both terms, out of the both terms, and factorize out. Came up with the radius at 2 times the tangential velocity at 2 minus radius 1 tangential velocity at 1. This is equal to your, let's say, torque. The last thing we came up with is this. Torque is dm dot times this, and we said that the power in previous slides we said that power is nothing but m multiplied by your torque. So you come up with this E of shaft, power of the shaft is equal to omega m dot r2v theta 2 minus r1v theta. One minus sign in here. You have to consider this minus sign in equation. Why we are using this, we will read in the next slide. We will find out why do we have to. Probably may do it as an exercise. If you put this minus sign, it's actually dealing with the sign of the work that you are dealing with. Whenever the work is positive, whenever the work is negative. Remember, when you have a positive work, it means that your fluid does work on in. Whenever you have negative work, it means machine works on the. That's why we are using this negative sign in here. Because if you have a compressor, you have to put this minus sign, then you will end up with the power that is positive. When you have EP shaft self negative kinetic give you positive sign. Okay, we we end up with the equation number 1, and if you integrate the equation number, integrating this from point, we'll find the power of shaft is, and we call the thing as the equation for turbomachinery. In here, what is happening is that you have you have a machine. You already know that what is axial machine. Your axial machine, and you remember that in axial machine, radius is not changing too much. So the radius at station 1 is equal to radius at station 2. So if you call r omega as 2, then what will it be? Minus power of shaft is equal to what? 2 d theta. What is happening for radial machine or centrifugal machine? In radial machine, you have a difference between inlet and outlet. So you 1 omega as u1 or 2 omega as u2. Then you have shaft power equal to u2 v okay. Now if we go to the third equation, which is our energy equation, see that what is the energy equation? You remember we said that Q minus delta W is delta E dE. So if you write it for an open system, you need to write everything in rate form. So in the rate form, you're writing it like this: Q dot energy change is actually the enthalpy change from 1 to 2. So you have this with the mass flux because it's an open system, and you have two rates of the work. Rate of the work is called power, right? Work per unit time is power. You have either a shaft power or shear power. Shear power is friction, loss of energy. Shaft is giving some power. There is loss of this power inside shear power. You already know that your enthalpy is internal energy plus P nu. If you assume that your machine is adiabatic, and if you assume that your shear is very, very smaller than your shaft power, then you will come up with the number 3. P shaft is m dot 1 minus h. We call this h0 or h naught. Then if you combine equation 2. Where is equation 2? Equation 2 is actually Euler equation for turbomachinery. In equation 3, then you will get equation 4. Normal for liquid handling machines like hydrogen pumps in rockets or fuel lines in aircrafts or the hydraulic pumps for the surface of the aircraft, aileron rudders, and they are handling liquid. Okay, so for liquid handling machinery like pumps, it's often they are using head rise in meters instead of the enthalpy. So enthalpy is used often for gases, but for liquids we are using the head rise. So let's have a look at the final session for today, which is the process representation on the enthalpy entropy diagram and the efficiencies. Remember it again from your dynamics and dynamics courses when you were compressing or expanding uh, gas from point 1 to point 2. Actually, you were assuming that it is either an ideal process, which is isentropic compression or expansion, or it was real process, which was not vertical line. And based on these, in your thermodynamics course, probably you've seen that you were defining the compressor or turbine as the ratio of ideal work to the actual work. The ideal work, if you remember from the first law, we said that it is isentropic or it is adiabatic. So there is no work, there is no heat transfer. So Q minus WH, right? If there is no Q, so your work is H, delta H. I mean, why we write it the ideal work as difference between ideally is going vertically, so it's going from H01 to H02. S stands for isentropic. This difference between 2 and 1 ideally, and actually it goes to some point, some another point, which is H02. So it's H02 minus H0. If you write it as H, this H is enthalpies. If you write it as CT0, and then using the isentropic relations between P0 and P0, and if it goes 0, which I will give as a homework to you, just remember these stuff and come up with isentropic efficiency of the compression or compressor is defined by this. You know, the gamma is the specific ratio and R is the gas constant. From 4 and from 4 you had the difference between the real states of point 1 and 2 as minus P shaft over m dot. From 6 you have this, so if you combine these you will end up with relates shaft power in a compressor to your states at 1 and 2, including the efficiency of the compressor. Same is actually applied to the turbine. So in the turbine, it expands the flow, so it reaches from station 4 to station 5. Why we call them 4 and 5? Your propulsion and jet engine nodes. Really, we are numerating the stations, the jet engine like this. So inlet of the turbine was 4 and the outlet was, I call it 4 and 5 in here. The inverse is happening, expansion is happening. And based on this, we are defining the turbine as well. Actually, these efficiencies are called isentropic efficiency or total to total efficiency. We are using them where we are interested in the jet, exit jet. But remember, for turboshaft engines, that there is no need for jet velocity. We were defining total to static efficiency of T05S, we are using T5. Why we say that any kind of kinetic energy turboshaft engine is actually a loss for us. Just need to minimize the exhaust. By this, we're gonna end today's. And from the don't forget to do the homework for the session. And, next lecture, we're gonna start with similarity, and then we cover the similarity. We are going to phase of axial flow compression.